Now, bad news. It used to be, I don't know, 6 years ago now, VST, DCT were included in the basic MATLAB package that you have. And then they took them away and they put them in, I think it's a signal processing toolbox. So you don't have access to them unless you buy that toolbox. Okay? So, kind of an interesting move. I've always expected that eventually at some point MATLAB will sell, here's MATLAB. And then you try to do backslash. Oh, what you need is the backslash toolbox. Oh, you wanted to plot that. Well, how about the plot toolbox? Oh, you have FFT. Well, how about the FFT toolbox? Haven't quite been that bad, but there's a lot of stuff that's got shipped out to toolboxes, including these here, and I don't know why. These should just be in the standard package. That's dumb. I'm saying right here on TV, MATLAB, you're dumb. I hope they watch that clip. But there you go. You can get access to all of these things. And it's as easy as this. And if you want to do the inverse, you just put an I in front of it. So like if you have the pad transform, here's its inverse. That was a really bad joke. Get it the iPad. Okay, anyway. Okay, I'm sorry I had to explain that, but all right. Remember, I'm trying to get you to yell at the end of class. And whatever it takes. Okay, so there we go. Those are our transforms. Now, a couple things. I want to really emphasize the following point, by the way, about the Fourier transform and how we're going to use it. So this is what we're going to work with. And let's come back to this first slide. The power of the Fourier transform, or any of these, discrete cosine, discrete sine, is this formula here, ultimately. And the speed. And we'll talk about speed in the rest of the lecture. But let's talk about what this means. This tells you relationship between derivatives and the functions of the derivatives. How did we do derivatives up to this point? When we were taking derivatives with finite difference, what we relied on is neighbors. You discretize, you see what the neighbors are doing, and from your neighbors you calculate your derivatives. Right? So what it was is you relied on local information. If I'm at this point in X, to evaluate my future or to evaluate what's happening around me, all I need to know is what's happening with my local neighbors. Way down on the edge of the domain is another part of the domain that doesn't talk directly to this point. It talks to this point through neighbors of neighbors of neighbors of neighbors, and they all connect, right? But ultimately, it's local. That's the important thing. Now, this says something completely different. This says, if I want to calculate derivatives, I just multiply by ik, but I take the function itself, and what I'm really doing is I'm working with a bunch of Fourier modes. So let's go back over to here. And I'm going to project all my information onto these modes, and when I take a derivative, I'm multiplying these modes, and these modes are global. It lives on the whole domain. So when I take a derivative, and I want the derivative, this point here, when I take that derivative of Fourier transform, it uses all information on the whole domain. Because the frequency content, the way you find frequency content is you figure out, I have this size of domain, what are the frequencies sitting in that whole domain? You cannot sample locally. You sample the whole domain, here's the frequency content, so when I do Fourier transform, it's global information is being carried into this spot. It's a very different architecture of how you're doing this information. Okay? That is really critical that you understand. And for emphasis, we have a drill. Okay. Okay. Good? You understand? That's good. Yeah.
So if you use an FFT but set the boundary conditions equal to 0, then that's the same as doing a DST, right?
Yeah, in fact. Okay, so let's talk about this for a moment. I have the FFT available to me in MATLAB. And I say, well, really what I want is, let's say, a discrete sine or discrete cosine. If you basically took a domain, imposed 0 boundaries, you could use the FFT. And it would basically do is, if you pose this kind of condition as this, it would basically throw away all the cosine coefficients. Right? You'd still be doing the computation. Oh, that coefficient is 0. So you'd still be paying extra work for it. But if it's n log n, it's not so bad. So you can still use this to do this, because eventually at the end of the day, you're just trying to throw away these coefficients here or throw away these coefficients there. Okay? So if you impose a symmetry, and in fact what you do know about sines and cosine rays is that you have even and odd symmetries. That's another way to do it in your problem. You can just simply say, I'm going to solve on a domain 0 to L. How about if I solve on the domain negative L to L, and my initial condition will be even or odd. So whatever it is, my initial condition I want on 0 to L, I'll impose the antisymmetric or symmetric version on 0 to minus L, and just do the computation with FFT. And because I'm imposing symmetries, it will just kill off one or the other. It's another way to do it.
You do that for every L, like you say f of minus n equals fn if it's symmetric or...
Yeah, so now your computation is twice the domain, but because you've posed initial symmetries, either even or odd, it will just basically, as you start to solve, it will zero out all of these or zero out all of these. And then at the end, you throw this all away, and you just keep what's on 0 to L. So it's just extra stuff. So it'll cost you more time, but fine. It's free. Not free. It's free with the MATLAB, and then you have to pay the extra for the toolbox. Okay? Okay. So that's comment 1. But remember, we are working on global basis functions. And what's really important, by the way, about the global basis functions is when there's going to be, so there's 3 issues here. So, okay, I lied. I said there's 2. 1 is this. 2 is the speed. But 3 is the accuracy. When you're working with these global functions to define derivatives, your accuracy is beyond any algebraic order. When we do a finite difference, and you say, take this point, use my neighbors to calculate a derivative, you have a scheme that's order delta x squared, or order delta x fourth, some delta x to some power, depending on how many neighbors I pick. This is exponentially accurate, e to the delta x type behavior. And so it's beyond all orders. So the accuracy properties of FFT are tremendous. And partly it's because you're using global modes as opposed to local information. Okay? All right. So there you go. That's kind of the idea. Now, the last thing we have to address then is, if we're going to be using this, and we have this kernel, then the real question is, if I'm doing this evaluation, it seems to be, at least on the face of it, order n squared. So where do I get the f in the FFT? The first f, not the second f. Okay? Okay?